Okay, so I want to look at some more examples of related rates here. And so I know I'm jumping around a bit, but this is example six. And so if you read through example six, okay, so it's we have a different shape now. We have a cone, right? So sand is falling off a conveyor belt in the shape of a conical pile at a certain rate. And again, I'm already picking up on the context of this rate since it's cubic feet per second, it's a volume. And so if you're not quite sure what's happening here, so let me go to pen. So you've got maybe a conveyor belt here, and then sand is falling off and it's making a pile, right? Like maybe it's at at a concrete factory or mill, or I don't know, something where you have sand, right? And the sand is making this pile. It could be for whatever reason it's creating this pile. Okay, now there is a relationship that says the radius of the pile is always 3 times the height. So that's going to be important a bit. And I give you this formula. And like I said, on the AP exam, you look at the trend in the past few, well, actually almost decade now, they've been really good about giving you geometric formulas because they're trying to test you on calculus, not necessarily do you remember your geometry formula. So I'll kind of follow suit with that. So it says, find the rate that the height is changing when the radius is exactly 18 feet. So again, we have to introduce time, but this is the first time, no pun intended, that we have 2 variables. So unless we want to do product rule, because r is a separate variable being multiplied to h, we should use this relationship that says the radius of the pile is always 3 times the height, right? It's always 3h. So we can either solve this for h in terms of r, or r is already in terms of h. And if you look up question A, it says find the rate that the height is changing. So we probably want to keep heights in there. So we're going to say r is in terms of h, and we're going to sub that in right there. So that way, that's going to avoid using the product rule. So I'm going to say, okay, well, volume equals 1/3 pi, and then 3h as a quantity squared times h, right? Because again, I'm trying to eliminate having r's and h's. So let's simplify first. 3 squared is 9. 9 times 1/3 would be 3 pi. And then I'd have an h squared, another h, so h cubed. So as long as I have that relationship of the radius to the height, then this equation is perfect for this particular problem. So we're going to ddt both sides, right? So introduce that rate. So that means that this is dv dt equals 3 times 3 is 9 pi h squared times dh dt. Okay. So then remember this dv dt we got here. It says it's changing at a rate of 72 pi cubic feet per second, and it's falling off it, and it's creating it to make it larger and larger and larger. My point being that is a positive 72 pi equals 9 pi, and then we want to know what the height is. And it says when the radius is 18 feet, but that's okay because we have this relationship that the radius is equal to 3 heights. So that means that would have meant the height would have been 6. So then I have 6 squared here, and then dh dt is the rate that the height is changing, and that's what we're looking for. So 6 squared is 36, and what I think I might do, rather than trying to multiply 36 by 9, I'm just going to kind of get a heads up here and realize if I divide the 36 across first, I know that 72 divides by 36 twice. And in fact, if I divide the pi across as well, that's nice, right? It crosses all that pi. So then 72 divided by 36 is 2. So I can kind of do this without really needing a calculator. Dh dt, which means divide by 9. So it looks like 2/9. So 2/9 is equal to my dh dt. And remember, it's a height. So the units I should measure this are linear, which I believe are feet. So it would be like 2/9 feet per minute, I want to say, or is it per second? Let's look at our rate up there. Per second. Okay. So then we change that to per second. So, it was smart, I think, of us to make sure we did that by eliminating one of the variables. Now we can do the other one too, because now it's asking for the rate the radius is changing. So if I start with my volume equals 1/3 pi, leave r squared, but now up here, so, one more step. If r equals 3h, that means r over 3 equals 1h. So I'm going to substitute this h for r over 3. That way I can solve the rate the radius is changing. So then that's r cubed, and that's another 3. So I get volume equals 1/9 pi r cubed. And then when I do my derivative, introduce the d dt, right? Introduce the rate, or do the operator, take the derivative. So that's dv dt equals 3 comes down times 1/9. So that's 1/3 pi r squared, and then the rate the radius is changing, dr dt, which is what I'm looking for. So here I know 18 is that same instant, the same moment of time, and that represents a radius measure. So I'm good with that. So dv dt is equal to 1/3 pi 18 squared dr dt. Oh, and I realized I still know my volume, right? My volume is still that same 72 pi. Wow, I almost have that lined up. 72 pi. Okay, so I know the pi's will cancel, so that's nice. And then, so I know I have 18 squared, which is 324, and then 1/3 of 324 would be 108. Because, right, if you have 324, 1/3 of it, that's really easy to divide out, 108. So I get 108 times dr dt. Now divide the 108 across, and so if I do that, I get 72 over 108, and I know that that's divisible by, I want to say 36, right? Because 336s is 18 as 108, so this is 336s, this is 236s, so that's a 2-to-3 ratio equals dr dt. Or remember, our label should be feet, so this should be 2/3 feet per second. So that's the rate the radius is changing at that instant, and the height is changing at 2/9 feet per second. All right, but here's the thing. So we know that the if you think about how does 2/9 compare to 2/3, right? So if I think about how does 2/9, let me pick a different color here. How does 2/9 compare to 2/3? Like, what is that ratio? Because 2/9 was like the height, and 2/3 was like a radius, rate changing. Well, 2/9 divided by 2/3 could be thought of as 2/9 times reciprocal, so like 3/2. So the 2's cancel. So, it's a 1-to-3 ratio. It's 1/3. Well, guess what? Wasn't the height to radius change also? Like, wasn't that always a 1-to-3 ratio, right? I mean, think about that. If our cone is forming such that the radius is always 3 of the height, then you could have easily just ddt'd that equation, right? I mean, there's no reason why you can't ddt that. So if I put that in parentheses and I ddt, well, that's 1, but it's dr dt equals 3 dh dt. In other words, if I know what the dh dt is, if I multiply it by 3, right, I will get dr dt. Or if I think about comparing the rates, if I always have to maintain a 3-to-1 ratio, then my rates have to be a 3-to-1 ratio. So I kind of forced you to do this problem twice, right? Because I wanted to practice that related rate component. But in reality, as soon as you found that the rate that the height was changing, if you just tripled it, if you took that times 3 dhdt's would have been 1 dr dt according to that relationship. So we got that. So, but like I said, now you know that. So now you don't have to always go through it twice if you have a cone and you know that relationship between the radius and the height. But for this particular example, I wanted you to go both, both ways just to practice that extra step. So sneaky Mr. Brown. Okay. Thank you for following along. And if you have any follow-up questions, certainly come in and see me in the office hours.